Hello. In this demonstration, we present large-scale program evolution for full executable TSP solver, showing how LLM-guided code mutations and empirical selection can systematically improve both tour quality and runtime. The traveling salesman problem is one of the most well-known challenges in combinatorial optimization. The goal of TSP is to find the shortest possible route that visits each city exactly once and returns to the starting point. Despite its simple formulation, finding the optimal solution is extremely computationally demanding, especially as the number of cities increases. TSP is a cornerstone of logistics, manufacturing, and planning optimization, enabling companies worldwide to save billions of dollars each year. Let's look at the results. The current state-of-the-art Yimeng Min et al.'s UTSP solver achieves an average tour length of 23.39 on 1,000 node instances. Our evolution ran for nearly 8,200 iterations over about a month, with most of the time spent evaluating candidates in parallel on a 12-core CPU. In each iteration, every candidate solver was tested on 128 predefined 1,000 node instances sampled from the 2D unit square. Under our evaluation protocol, the full set of 128 instances had to complete within a strict 160-second wall clock budget, so the instances were run in parallel across the 12 CPU cores. You might notice that the mean tour length sometimes increases. That's expected because the optimizer targets a combined score, not tour length alone. The combined score includes average tour length variance, and average execution time. For example, at this point, the system found a solution that runs nearly 40 seconds faster, which improves the combined score even if the mean tour length slightly increases. Let's also inspect key changes of some intermediate solver variants. Another useful view is the population behavior across islands. We use 3 islands, and this plot shows the average tour length of programs within each island over time. As we can see, the island averages often cluster near the current best value, just before a new breakthrough appears. As a result, the best version of the algorithm lags behind Concord by 33.2% less in terms of quality, compared to the original UTSP version. Next, here's a live example of how an evolved candidate searches for a better tour. On the left is the tour the algorithm is exploring right now, and on the right is the best tour found so far. To run evolution yourself, follow these steps. Clone a repository, which adds large codebase evolution support, a TSP evolution configuration, and code for parallel evaluation. Install the required Python packages and a C++ compiler. Set up your DeepSeek API key or use any other LLM provider. Finally, start the evolution. This demonstration presents the empirical results of applying program evolution to the traveling salesman problem using the OpenEvolve framework. By evolving full solver implementations and evaluating them at scale, the system produces competitive, fully executable solvers and illustrates how large-scale program evolution can systematically improve solution quality on large Euclidean TSP instances. Thank you for your attention.